Now, there's a second kind of experiment that now starts to illustrate the issue of non-locality, the issue that Bell talked about. And as I said, non-locality has to do with effects of an experiment done in one lab on an experiment done in another lab very, very far away, arbitrarily far away, according to the theory. And so in order to illustrate this, I need more than one particle. I need a particle that's going to be sent to Alice in her lab and another particle that's going to be sent to Bob in his lab far away. And it turns out that these pairs of particles can be in special states, entangled states. The one that's usually looked at for a pair of particles, like a pair of electrons or a pair of neutrons, is what's called the singlet state. And again, quantum mechanics makes very specific predictions about the outcomes. Sorry, the dog is whining. About the outcomes of experiments done on these pairs of particles, even when Alice and Bob are arbitrarily far apart. So let's just talk about that. In the singlet state, what are these predictions? Well, it's that if Bob and Alice, the only one I'm going to talk about now, they're more interesting ones, but if Bob and Alice set their two Stern-Gerlach magnets in exactly the same direction, if they both check in the x direction, if they both check in the z direction, then the predictions of quantum mechanics are very simple. It's that 100% of the time, Alice and Bob will get opposite results. If Alice gets up, Bob will get down. As for whether it's Alice getting up and Bob getting down, or Alice getting down and Bob getting up, the theory doesn't make a strict prediction. It says half the time it'll be like this and half the time it'll be like that, but all the time they'll be exactly opposite. They'll be anti-correlated. All right, this is an example of a kind of correlation that was first noticed by Einstein and was made the centerpiece of a famous theory that Einstein wrote with Podolsky and Rosen called the EPR paper in 1935. Now, you might think, well, there's nothing very puzzling about that, right? Why should I be puzzled that whenever Alice sees one thing, Bob sees the other? As people say, if I take a dollar bill and rip it in half and send the two sides off, one to Alice and one to Bob, then always they'll get different sides, right? One will get one side of the bill and the other will get the other side of the bill. And there's nothing particularly spooky or non-local about that. So these phenomena, this particular phenomenon of this perfect anti-correlation could be explained in a purely local way, where there's nothing spooky, no spooky action at a distance, as Einstein would have said, going on. But it turns out that what Bell showed, and I'm not going to go into that proof here, is that although you can have a local explanation of that particular experiment, if Alice and Bob, instead of measuring in the same direction, start to measure in slightly different directions, if they adjust their magnets so that there's some angle between them, then the quantum mechanical predictions cannot be explained in a local way. These perfect correlations could be, but as a matter of fact, in this pilot wave theory I've been talking about, they're not. In the pilot wave theory, it is the case that you have a kind of physical non-locality here. And I just want to go through this. If you're interested, it's nicely explained by David Albert in his book, Quantum Mechanics and Experience. So what's the situation? I have a pair of particles. I'm sending one off to Alice this way. I'm sending one off to Bob that way. The quantum state of that system is a singlet state, so I know what that is. In this theory, I also have the precise positions of the two particles. And you might think, well, it must be that always one particle starts out above the midline and the other particle starts out below the midline, and that's why this one goes up and that one goes down. But that's not correct. In this theory, they can both start out above the midline, or they can both start out below the midline. And then you might say, well, but then what determines which goes up and which goes down? And the answer, it's a very simple answer in the non-relativistic theory, is that the particle that gets to its detector first does what you expect. If it's above the midline, it goes up. If it's below the midline, it goes down. And the particle that gets to its detector second then is automatically required, or it follows from the equations of motion, that it'll do the opposite thing. Okay, so if in fact you did this experiment according to this theory, if you did this experiment and both the particles start above the midline, if Alice measures hers first or puts hers through her apparatus first, she'll get an up outcome and Bob will get a down outcome. But if Bob puts it through his apparatus first, he'll get the up outcome and she'll get the down outcome. So this is this non-locality. That is, in order to understand what happens in Alice's lab, you have to take account of what happens in Bob's lab. If Bob decides to be lazy and not do his experiment at all, then Alice will get one result, but if he decides to be very ambitious and do his early, Alice could get a different result. So you just can't predict what she's gonna see without taking into account what he does, even though he is arbitrarily far away, so far away that what he does cannot be communicated to Alice at signals that go the speed of light. All right, so the main thing is which of these two experiments happens first. Good. Now, that's the way the non-relativistic theory works. But you say, gee, that's non-relativistic. I want to transition. I want to somehow write this theory or adjust this theory to work with relativity. I want to transition to a relativistic theory. And the problem is that in relativity, in the standard way of understanding relativity, there is no time order between these two events if they're that far apart, if they're at what we call space-like separation. There's no fact of the matter at all. There's no physical fact which happened first. There's no time order. There's no, as we say, global time order that orders all the events in the universe, so that for any pair of events, you can ask whether A is before B or B is before A, or they happen at exactly the same time. That's a part of the structure that gets lost in relativity. It doesn't exist. It's technically, if you have a Lorentzian metric in a relativistic setting, there is not what we call a global foliation, a kind of global time structure that orders events in terms of earlier and later. Go on. So now you say, but wait a minute, in the non-relativistic theory, I really needed this time order, right? It was important physically whether Alice or Bob does their experiment first. And now I want to somehow produce such a theory in a relativistic setting. I no longer have this global foliation. What am I going to do? And one answer, one that I have always thought was kind of reasonable, is say, well, if I really need it physically, I'll just put the foliation back in, right? I will add it, even though it's not part of classical, special, or general relativity. I'll put it back in, and I'll be, in order to use it to implement this non-locality that Bell discovered. Now, I've been arguing for decades that this is a reasonable thing to do. Most physicists don't like it. The reason they don't like it isn't that they argue it can't work, but that it's this kind of comment that Russell made about certain philosophical theories, where he says, well, this theory seems to have all the advantages of theft over honest toil. It just seems too cheap or too easy to say, well, I could use a foliation. I don't have one. I'll just add one. Now, I personally have always been a little puzzled by this, because it seems to me that to say that something's cheap is, as far as its cost goes, a good thing, right? It's better if things are cheap than expensive, assuming they work perfectly well. what would happen in the case I just gave you is you can start with a relativistic space-time that has a light cone structure and all the normal structure of relativity, and then add to it a foliation, and now you have a new structure. You're not going back to classical physics, you're going forward to yet a new structure. People don't like it. Okay, I'm not even going to argue about that here. I've gone through all this to explain why one would want, just in order to be able to implement quantum theory, you would like a foliation. It would be a nice thing to have. Now, the rest of this talk is going to be this new stuff which you've never seen before. So suppose we don't do what I just suggested, that is, start with a relativistic space-time and add a foliation to it. But suppose we start with an entirely different structure, completely different, absolutely non-relativistic looking structure, and see whether the relativistic structure can naturally emerge from it. That is, even though at a fundamental level, the space-time structure does not look at all relativistic, maybe in a very simple and comprehensible way, something that does look relativistic can emerge from it. That's going to be the scheme now. And I'm going to show you that this actually can happen. And it can happen where the underlying or the exact or precise structure is as non-relativistic and non-classical in every respect as you can imagine. That even in that situation, in a very natural way, something that at macroscopic scale kind of looks classical and looks relativistic can emerge, and can emerge in an extremely natural way. So that's what the rest of the talk is going to be about. Now, the place to begin here is, let's imagine that space-time is discrete. And this is already making a change from all classical physics. Because in classical physics, you start with space, say, being thought of as a Euclidean space, which is a continuum. And if you do general relativity, the first thing you pull off the shelf mathematically to describe space-time is a four-dimensional differentiable manifold, which is a continuum. But we've known from antiquity, people have thought from antiquity, maybe space and time are not continuum. Maybe they're discrete. Maybe they have a kind of atomic structure when you get all the way down to the finest possible scales. And we all understand how something that is discrete at a fine scale can nonetheless look continuous, like if you have good resolution on your laptop, it might look like there are nice continuous lines on your screen, but in fact, all there are pixels, right? Discrete pixels that are either on or off. So the general idea that we can't tell by any casual examination whether space and time at a fundamental level are discrete and continuous, that's been recognized since antiquity. But I don't think the discrete possibility has been explored enough. Certainly not since Newton, not since Galileo, not since essentially the beginnings of modern mathematical physics. Continua were always taken to be the structure of space and the structure of time.